All right, guys, so welcome back. Today we have kind of like two lessons in one, mostly just because, well, actually, here's what's going to go on with the rest of the year. So we are on unit 4. There are 7 units in this class. Clearly, with the like month we have left of school, we are not going to get through those other 3 units. We're going to breeze through them. We are going to get to the important parts, and that's it. And today, what I want to do with y'all is get to the important parts of Unit 4. So, the important parts, in my opinion, are these parts down here at the end. But in order to figure out how to do these, we need to be able to do this stuff first, which is why I need to teach you graphing these rational functions just a little bit before we can get to the inverses of rational functions. And so, yeah, that is what we're going to do. We're going to touch a little bit on graphing these rational functions. Typically, we'd spend more time on this, but we just don't have that time due to the current situation. So that's what we'll do. All right, so graphing rational functions. We know how to simplify and solve rational equations, which y'all did last week. But what do these functions look like when they're graphed? So this graph over here on the right is a rational function when it's graphed. That is the graph of this right here on the left, y equals x minus 1 over x minus 2. So that is the graph of that function. And these dashed lines on the graph are called asymptotes. So ASYMPTOTES, asymptotes. So the dashed lines, these gray ones, are asymptotes. The vertical one, so the vertical that's up and down, this gray one is at x equals 2. So x equals 2. And the horizontal one is y equals, so horizontal is y equals 1. So y equals 1. All right, what is significant about the vertical asymptote? I truly don't know what it's looking for there. So we are just going to ignore that question and pretend it's not there. So what's the x-intercept? The x-intercept, well, we just said that. It's x equals 2. Oh, no, it's not. That's the asymptote. My bad. X-intercept of the graph. So the graph is this bluish, purplish line here. The x-intercept is where it crosses the x-axis, and it's that point there at 1. So the x-intercept is x equals 1. What's the y-intercept? Well, it's where this bluish purplish line crosses the y-axis. Y-axis is up and down. And it's right there at about 1/2. So the y-intercept is about y equals 1/2. What are the 2 points we know exist on the graph? Well, they put 2 points in green here. They put this one that I already circled, that point right there is 1, 0. So 1, 0. And they also put this other point up here in the green, and that is the point 3, 2. So the other point that is on the graph is 3, 2. So those are the 2 points that we know exist on the graph. Okay. Then it's asking what is the domain and what is the range. So if I look at my graph, my domain is left and right, and the domain, it goes all the way on to the left forever and all the way onto the right forever. However, right here at x equals 2, there's that gray line because it doesn't exist at x equals 2. It's not a blue line. It's not that bluish purplish line. It's a gray line, which means it's not actually there. So x equals 2 is not part of the domain, but everything else is. So the domain is everything but x equals 2. So the way we're just going to say this is x does not equal 2. Because x can equal everything else, but x does not equal 2, whatever it is. And the range, that's up and down. So the range is going to be the same thing because it can go all the way down to negative infinity, all the way up to positive infinity, but at y equals 1, it stops existing. So the range is everything except y equals 1. Y doesn't equal 1. Y can equal everything else, but y cannot equal 1. All right, so that is the interpretation of a graph of a rational function like this. And I know I'm going through this a little bit quickly. I said I would, because this is not the part I want you guys to be taking. I mean, I do want you to take this away. I do want this to be a takeaway from this lesson, but it's not the more important part, in my opinion. So, guidelines for graphing rational functions. So start by factoring the numerator and denominator, find your x and y intercepts, find any asymptotes, and then plot at least one point between the asymptotes and one beyond each vertical asymptote and x-intercept. And that's what they did there. That's why they were like, oh, what are the 2 points we know exist on the graph? So you could identify those other 2 points. All right, so domain, range, x-intercepts, y-intercepts, y'all know what that means. Y'all know the definition of these. However, this part here, this part is where it gets important. This part is the part that we're going to need to use. Vertical asymptotes. To find the vertical asymptote, set the denominator equal to 0 and then solve. And then the values of x that you get, those are vertical asymptotes. One thing I will say about the vertical asymptote, or actually, no. The reason we need to find the vertical asymptotes is because this will help us determine the domain, because then we know what values the domain cannot exist at, because there are asymptotes there. And the horizontal asymptotes will help us determine the range, because it tells us what values the range will not exist at. And the horizontal asymptotes, there are 3 rules, or 3 possibilities. So if we have a rational function like this, if the numerator's degree is less than the denominator's, the horizontal asymptote is y equals 0. So here, this f of x equals x over x squared minus 9. What it means by the numerator's degree is less than the denominator's. So the numerator is x, which is x to the first power, and in the denominator there's x squared. And I'll make that x to the first power. So I have x to the first power over x squared. Since 1 is less than 2, so the numerator is less than the denominator, the horizontal asymptote is 0. And the same here, we have 3x squared over x cubed. I don't care about anything else after that. All I care about is that x squared and that x cubed. And I see that the 2 is less than the 3. So since it is less than, the horizontal asymptote is 0, once again. So that's the first case, if the numerator is less than the denominator. The second case is if the numerator and the denominator have equal degree. So the horizontal asymptote where a and b are the lead coefficients of the numerator and the denominator. So here we have x over x minus 9. These are both x to the first, so the degree is equal. And this is 1x to the first, and this is 1x to the first. So the horizontal asymptote here is going to be, I'm just going to take this 1 and this 1, the number in front of the x. And that's only if the degrees are equal. So it's 1 over 1, or just 1. The horizontal asymptote of this function is going to be 1. And here we have x squared and x squared. So they have equal degree. So now I'm taking the 4 over 2. So the horizontal asymptote is 4 over 2, which is 2. So the horizontal asymptote of 4x squared plus 1 over 2x squared minus 3 is 2. that means that is the place where the range will not exist on this equation, on this function. Okay, and then the third case we're going to see is if the numerator's degree is greater than that of the denominator, then there is no horizontal asymptote. So we don't even have to worry about that, and the range will just exist for all possible numbers. So here, our first example, we have f of x equals x squared over x minus 9. So that's x to the first. Since 2 is greater than 1, then it's greater than, and there is no horizontal asymptote. And same here, we have x to the fifth over 3x squared. The 5 is greater than the 2, therefore no horizontal asymptote. So personally, I do think that, like, I'll make it like, we'll go green. Nope. Okay. This part right here is super important. So the vertical asymptotes, the horizontal asymptotes, you're going to want to know how to find these, because these are going to help you with the domain and the range of these inverse functions that we're going to see later. So, yeah, that's basically just, I'll even star it. Know this part. I think last semester I even had my students, like, I even printed like this box out for them, and I was like, know this or have this on you when we're doing these things. So we did that. All right, so here's some practice with the horizontal and vertical asymptotes. Let's see. So to find the horizontal asymptote of this first one, let's see. The degree of the numerator is 1. The degree of the denominator is 2. So the numerator's degree is less than, therefore the horizontal asymptote is x equals 0. No. Horizontal is y. My bad. Horizontal is y equals 0. Vertical is x. Horizontal is y. And then we have the vertical asymptote. So the vertical asymptote is the zeros of the denominators. So set the denominator equal to 0 and then solve. So I have x, you know what, I'm actually going to go a little bit smaller with this. So I got x squared, minus 2x minus 3 equals 0. So this is a quadratic, and I can solve this by factoring it. So I need to find two factors of negative 3 that add up to negative 2. And those two factors are going to be negative 3 and 1. So that gives me x squared minus 3x plus 1x minus 3. And then I'm going to group. Between x squared and negative 3x, I can pull out an x, and I'm left with x minus 3. And between x and negative 3, I can't pull out anything, but I got to pull out something, so I'm pulling out 1. And that leaves me with x plus 1 times x minus 3. And that equals 0. And if x plus 1 is 0, then x equals negative 1. And if x minus 3 equals 0, then x equals positive 3. So the two vertical asymptotes of this problem here were negative 1 and 3. All right. Yeah, let's go on to the next one. So this next one is x to the third over x squared, and 3 is greater than 2, so this one has the numerator's degree is greater than, meaning that there is no horizontal asymptote. However, the vertical asymptote, and this one's going to be a little bit tricky because it's something that you'll have to recall from like unit 1. So we just got to set that denominator equal to 0. So we're saying x squared minus 1 equals 0. And you may recall this, but instead of factoring this like a normal function, since there is no like b, it's just x squared minus a constant, this is a difference of squares because x squared is a square and 1 is a square because it's 1 squared, and it's a difference because there's a minus sign. Meaning the way we factor this is simply x plus 1 times x minus 1. And if you don't remember that, that's okay. It's from like unit 1. We touched on it briefly, and you could factor this the normal way. It's just going to be a little bit trickier. So yeah, don't worry about it as much. Don't worry about how I did that. It's just take my word that it's x plus 1 times x minus 1. So if x plus 1 is 0, that means x equals negative 1. And if x minus 1 is 0, that means x equals positive 1. So negative 1 and positive 1. And there are the two vertical asymptotes for this. What's it called? Function, rational function. Yeah. Okay. And finally, this third one here. This one has 2x squared over 3x squared. So that x squared and x squared, that's the same degree, meaning that we're just going to look at the coefficients of the numerator and the denominator. So the horizontal asymptote is y equals, and I'm going to take this 2 and this 3, y equals 2/3. That's my horizontal asymptote. You are never going to have more than one horizontal asymptote. Vertical asymptotes, you can have as many of those as they want to give you. But horizontal asymptotes, the maximum amount of horizontal asymptotes you'll have is just one. All right, and then the vertical asymptote, so we got to find the zeros. We got to find the zeros of 3x squared minus 5x minus 12. All right, sorry. Okay, just checking on something. Okay, so I am going to make this pretty small because it's going to take a bit to find those zeros. So I have, what is it? Yeah, 3x squared minus 5x minus 12. That means I want to find two numbers that are going to multiply to be 3 times negative 12 is negative 36, but they're going to add to be negative 5. And those two numbers that are going to multiply to be negative 36, but add to be negative 5, I believe it's negative 9 and 4. Yeah, negative 9 and 4. So I'm taking this and I'm saying 3x squared minus 9x plus 4x minus 12. Then I'm going to group. So 3x squared minus 9x. Between those two, I can pull out a 3x. And I'm left with x minus 3. And between 4x and negative 12, I can pull out a 4. And I'm left with x minus 3. So that gives me 3x plus 4 times x minus 3. And, all right, I have to set that equal to 0, meaning I have to set this equal to 0. So if 3x plus 4 is 0, let's see, subtract 4 from both sides. That gives me 3x equals negative 4. And then divide by 3. So x equals negative 4 thirds. So x equals negative 4 thirds. And then we have x minus 3 equals 0. So if x minus 3 equals 0, x equals 3. So the vertical asymptotes of this one were x equals negative 4 thirds and x equals 3. All right. Do I even want to do this part here? No, I don't. Well, you know what? I'll do one of them. Yeah, I'll do one of them. Yeah. I don't like example A. I do like example B though. Yeah, example A had too much going on. Okay, example B. That's the one I'm going to do. So graph the function and find the domain, range, vertical and horizontal asymptotes, and x and y intercepts. So, my function is f of x equals 2x plus 1 over x minus 3. So the horizontal asymptote, to find the horizontal asymptote, that's the one where I have these rules. And it was 2x plus 1 over x minus 3. So these are both degree 1. They have the same degree, which means I'm taking 2 over 1. 2 over 1 is just 2. So my horizontal asymptote is y equals 2. My vertical asymptote, that is going to be the zeros of the denominator, and my denominator is just x minus 3. So if x minus 3 equals 0, x equals 3. And I'm just going to move that down there. X equals 3 is my vertical asymptote. And I'm going to go ahead and put those lines on my graph here. I'll choose a color different. So y equals 2, that is going to be like right there-ish. And x equals 3, that's going to be here. So there is my graph. My x-intercept. So to find the x-intercept, hold on. The x-intercept, it says x-intercept is find by setting the numerator equal to 0 and solving. So that means my x-intercept, I'm going to have 2x plus 1, because that's my numerator, equals 0, and then solve. So subtract 1 from both sides. So I got 2x equals negative 1, and divide by 2, x equals negative 1/2. So there's my x-intercept. My x, and then negative 1/2. That doesn't sound right, but I guess it is. Okay, I'll take their word for it. Actually, yeah, no, that does look right. My bad. Okay, and then my y-intercept. My y-intercept is where it's going to be when x equals 0. So that means I have 2 times 0 plus 1 over 0 minus 3. Well, 2 times 0 is 0, plus 1 is 1. And then 0 minus 3 is negative 3. So my y-intercept is negative 1/3. So that's like right there. There we go. Let's see. What advice did it have for finding, oh it didn't, I was going to say, what did it have for finding the other additional points? So while I have this, I can identify my domain and my range. My horizontal asymptote was y equals 2. or no, my vertical asymptote was x equals 3. That's the domain. So that means my domain is x doesn't equal 3 because there's an asymptote there. My range is going to be y doesn't equal 2 because there's an asymptote there. That's it. That's all I have to have for my domain and my range. Okay. Not entirely sure what I'm supposed to put in this table here. Oh, yes I do. So we are supposed to look at our horizontal asymptote, or vertical asymptote, which is at x equals 3. And I need to pick a point to the left and to the right of that. So I can go with 2 and I can go with 4 because 1 is to the left, 1 is to the right of 3. So let's see. I have a 2 and I have a 4. And if I plug 2 into my equation, so I'm just going to do it down here, kind of small. So 2 times 2 plus 1 over 2 minus 3. 2 times 2 is 4, plus 1 is 5, and 2 minus 3 is negative 1. 5 over negative 1 is negative 5. So let's see, that gives me the point 2, negative 5. I wish I hadn't gone with gray. Oh, wait. Oh yeah, okay. I'm going to go with this like yellow color. So 2, negative 5. And then for the 4, I'm going to plug that in as well. I have 2 times 4 plus 1 over 4 minus 3 equals, well, 2 times 4 is 8. 8 plus 1 is 9. And 4 minus 3 is 1. 9 over 1, that's just 9. So I have the point 4, 9, which is like, okay, that's like 4, 8, so 4, 9 would be like there-ish. Probably a little higher up. Okay, yeah, 4, 9 is like there-ish. In retrospect, should have gone with 5, but whatever, doesn't matter. Okay, and then I don't know why there's a third option there. Oh, I do know why there's a third option. It's because sometimes you're going to have two vertical asymptotes, so you're going to have to test like multiple different points. So you're going to have to test like something that's all the way to the right, something that's all the way to the left, and something that's in between. This one only has one vertical asymptote, so we only need to test something to the left of it and something to the right of it. And we get those 2 points. And using those, we can sketch this graph. So, what is this one going to do? It's going to hug this this vertical asymptote. It always does, and it's going to go through these points that I've plotted because I plotted some points. Then it hugs the horizontal asymptote as well. And then it looks like it's going to come down from up here and do something like that. We don't know exactly what it's doing, but we do know it's coming down and it does hug the asymptotes. That's what it's called. So it's pretty much riding along those asymptotes, staying pretty close to them, but it's never going to touch them because that's what an asymptote is. It's a line that you're never going to touch. All right. So there was one example of graphing a rational function. Sorry, I'm like really out of it today. Whatever. Okay. We're not going to worry about this one. We're just going to get to our inverses of rational functions. So, an inverse function for f of x is labeled with f1 of x, and it's actually, you can't really see it, but it does say f negative 1 of x, So it is labeled f negative 1, not f1, and it's read f inverse of x. It contains the same domain and range elements as the original function, just switched. And the reason I want to do rational functions is because we've already done rational functions. You guys know how to do rational functions. Or not rational functions, sorry, inverse functions. We have done rational functions, but inverse functions, you guys were great at those. So that's kind of why I wanted to get to them. So the domain of f of x is going to be the range of f inverse of x. And the range of f of x is going to be the domain of f inverse of x. What that means is if f of x has a horizontal asymptote, that same line is going to be a vertical asymptote for f inverse of x, and vice versa. So yeah, hopefully all of that stuff you can read it on your own. It's coming back to you from when we did inverse functions in the first place, because it's all the same rules. So the first thing we got to do when we find these inverse functions, and I know that this one isn't exactly a rational function, this is a radical function, but we can still work with it. Okay, so the first step is rewrite the function using y instead of f of x. So the first step, so we're going to say y equals the square root of 2x plus 3. And then we're going to switch the x and y variables. And once you do that, we got x equals the square root of 2y plus 3. And then we want to solve the equation for y. So to solve the equation for y, let's see, I just want to get y all by itself on that right side of the equation. So since everything on that right side is underneath that radical, I'm going to square both sides to get rid of it. So let's see, that gives me x squared equals 2y plus 3. And that gets rid of the radical on the right side, squares on the left side. That's fine. I should have made that smaller. Is that something I can do? I don't know. Maybe if I hit style. Oh, wait. No, that just makes it literally smaller. Okay. Yeah, whatever. Okay. Sorry. Okay, that's not even smaller. X squared equals 2y plus 3. Then my next step, to get y by itself, I can't divide by 2 yet. I have to get rid of that 3 first, so I'm going to subtract 3 from both sides. That gives me x squared minus 3 equals 2y. And then to get y all by itself, I just divide both sides by 2. So that gives me x squared minus 3 over 2 equals y. So y equals x squared minus 3 over 2. And that is the inverse of the square root of 2x plus 3. So then step 4, replace y with f negative 1 of x. So what we're going to do is we're going to say f negative 1 of x equals x squared minus 3 over 2. That's all we got to do. And then make sure that your resulting inverse function is 1 to 1. If it isn't, restrict the domain to pass the horizontal line test. Y'all don't know what that means, and that's okay. 1 to 1 basically just means that for every input value, there's an output. For every output value, there's an input. And this one is 1 to 1 because there is no asymptote. Basically, it's just saying, is there an asymptote? And then it's saying like, oh, tell us what the new domain is or the new range is if there is. So there is no new range or new domain. So we're just going to say not applicable. Okay, so then we get to this next problem. And I actually quite like this next problem. So, first thing we're going to do is, well, what it said for step 1 was replace f of x with y. So y equals 2x minus 7 over x minus 3. The next thing I want to do is switch all my x's and y's. And there's two x's here, but we're going to switch them. So, and you may want to give yourself some room to work on this problem. So we got x equals 2y minus 7 over y minus 3. And now we have to solve for y. But there's two y's. So it's kind of difficult to tell what we're supposed to be doing here. But eventually, we are going to be able to isolate both y's into the same y. And you'll see how I'm going to do that. But for now, I don't see anywhere I can start with this. But the first thing that it looks like I might want to do is multiply both sides by y minus 3. Because if I do that, I will be getting rid of that denominator. Okay, they give us plenty of room to work there. So if I multiply both sides by y minus 3, that gives me x times y minus 3, and then that cancels out the denominator on the other side, equals 2y minus 7. All right, my next step here is, I'll take it to this nice watermelon color, distribute that x. Distribute it inside the parentheses. And, there's really no way to know what you should do next. It's just like, oh, what do I know how to do because I know some math skills. I know the distributive property. I know that maybe I can distribute this and something will come to me. So if I distribute this, we get, well, x times y, that's just xy. And then negative 3 times x is negative 3x equals 2y minus 7. That right side is staying the same. So now what I want to do is move all of my y's to one side of the equation. So I have an xy and I have a 2y. So I'm going to subtract that 2y from both sides to get xy minus 3x minus 2y equals negative 7. The next step after this one is to have only the y's on the left side of the equation. So I have an xy and I have a negative 2y, but I still have this negative 3x. And there's no y in that term, so I'm going to add 3x to both sides to get it out of here. So that gives me xy minus 2y equals, well, I add 3x to both sides, so I got 3x minus 7. And now, earlier I said we would be able to isolate our y's into just one variable. And this is the step where we do that. Because on my left side I have xy minus 2y. And the GCF between xy and negative 2y is y. So I can pull out that GCF now. So I got y, and then xy divided by y is x, and then negative 2y divided by y is negative 2. I got y times x minus 2 equals 3x minus 7. And instead of distribute this back out, earlier we distributed when it was with the x, but with this y, we just want to get it alone. And I basically have y times this thing, this x minus 2, equals this other thing. So to get rid of this x minus 2, all I have to do is divide by x minus 2, because it's just being multiplied. So when I divide by x minus 2, I'm left with y equals, let's see, I have 3x minus 7 divided by x minus 2. And this right here is my inverse function. And so the inverse of 2x minus 7 over x minus 3 is 3x minus 7 over x minus 2. The fourth step was replace the y with f negative 1 of x equals 3x minus 7 over x minus 2. And finally, restrict the domain. So we have to say if there are any vertical asymptotes, because the domain is vertical asymptotes. So to determine the vertical asymptotes, this is the part where or this is why I had you do that thing earlier. To determine what the vertical asymptotes are, you just have to find the zeros of the denominator. And the denominator is x minus 2. So if x minus 2 equals 0, that means x equals 2. That's the asymptote. And so the domain means is everything but the asymptote. So the domain is x is not equal to 2. And that's all you got to do. So yeah, it was just that denominator, that x minus 2, set that equal to 0, solve, and then say the domain is everything but that. All right, so there's that. And then we will try example 3. Example 3 is going to be pretty similar. So, first step with example 3, replace f of x with y, just like all the others. So y equals 25 over x plus 1. And let's see, that 25 over x, next step, replace or switch x and y. So x equals 25 over y plus 1. And that 25 over y, I can't really do much with it. Don't really see a way to isolate this y yet, but I do see a way to get rid of that 1 at least. So I'm going to subtract 1 from both sides. And if I do that, I'm left with x minus 1 equals 25 over y. And what I'm going to do now is, there's no point in bringing that x over. I already did something with the 1, and I can't get rid of that 25 because it's in the numerator. So what I have to do is multiply both sides by y. So when I do that, I have y times x minus 1 equals 25. And I know that on the last problem, I distributed once I did this step, but what I want to do is get y by itself. And there's a real easy way to get y by itself from this step. And the easy way is just divide both sides by x minus 1. Because I have y times x minus 1 equals 25. So to get rid of the x minus 1, just divide. So that means y equals 25 over x minus 1. And there's my solution. That means the inverse of 25 over x plus 1 is 25 over x minus 1. And we're going to, let's see, step 4 was replace y with f negative 1 of x equals 25 over x minus 1. And step 5 is identify the domain. So let's see, the denominator is x minus 1, set that equal to 0, add 1 both sides, x equals 1, which means my domain is x is everything but 1. That means if I plug, let me tell you why it's everything but 1. So let's see, if I were to have 25 over, and I'm going to plug in 1 minus 1. Hopefully you should see a problem with this automatically, because 1 minus 1 is 0. And you can't divide by 0. That's why the domain does not exist there. You can't divide by 0. So yeah, that's what an asymptote is. An asymptote is where the function tried to divide by 0 and it was like, wait, I can't do that. It doesn't exist here. All right. So, example 4 here, this one is different. We have consider the rational function f of x equals 3x plus 10 over 2x plus 5. And it's just asking, what's the domain of f of x? Well, the domain, again, set the denominator equal to 0 and solve. So 2x plus 5 equals 0. Subtract 5 from both sides. So 2x equals negative 5. And then divide by 2. X equals negative 5 halves. So the domain is everything but that. The domain is x is not equal to negative 5 halves. And the range of f negative 1 of x, so f inverse of x. So remember, when you take the inverse function, the domain becomes a range. So that means if this was the domain of f of x, the range of its inverse is going to be the same thing, except range is y. So we're going to have y is not equal to negative 5 over 2. Because this is the base function, this is the inverse function. Okay. So here, example 5, it says, which is the inverse function of f of x equals 5 over x minus 2? Show y. So we're just going to go through our 5 steps. Don't need to go through all 5. I'm just going to go ahead and switch everything. I'm going to switch x with y, and then I'm going to switch, or switch f of x with y, and then switch x and y all in one step. So that gives me x equals 5 over y minus 2. And I want to get y all by itself. Can't do anything with that 5. Can't do anything with that x. And that y minus 2, I can do something with that. So I'm going to multiply both sides by y minus 2. So that gives me x times y minus 2 equals 5. And this is one of those ones where the x is outside, so I'm distributing. So x times y is xy minus 2x equals 5. I am going to add 2x to both sides to get the y all by itself on this side. So xy equals 2x plus 5. And then to get y all by itself, I just divide by x. So y equals 2x plus 5 over x, or, well, since it's a numerator, you are able to split it up, and that gives you 2x over x is 2, 5 over x is 5 over x, so that equals 2 plus 5 over x, or 5 over x plus 2. That one's the inverse. Okay, and then this 6th example here, it says, show that they're inverses algebraically and graphically. Graphically, I'm not going to worry about it as much. The way you would show that is just saying, oh, this one has a horizontal asymptote here and a vertical asymptote here, whereas this inverse has the horizontal and vertical asymptotes the exact same, but just flipped. So, that's basically how you would show it graphically. And like I said, we're not really worried about graphing. Okay, So show that f of x and g of x are inverses. So it's telling me what the inverse is. But we have to prove it. So I have x minus 1 over x plus 5. So I'm just going to go ahead and knock out those first two steps. So I have x equals y minus 1 over y plus 5. My next step, I will multiply both sides by y plus 5. So x times y plus 5 equals y minus 1. Then I'm going to distribute my x. X times y is xy. 5 times x is 5x equals y minus 1. Again, we have to get all of our y's on the same side. We have to get all of our non-y's on the same side. So I'm going to subtract y from both sides first. So I got xy plus 5x minus y equals negative 1. And now I'm going to subtract 5x from both sides. And that is going to give me xy minus y equals negative 5x minus 1. And let's see, between xy and negative y, I can pull out a y. And I'm left with x minus 1 equals negative 5x minus 1. And then to get the y all by itself, just divide both sides by x minus 1. So y equals negative 5x minus 1 over x minus 1. And that is an equivalent form because basically it's like what they did was they took negative out of the numerator. So they just took the negative out of the numerator and put it out front. That works perfectly fine. So yeah, that's why f of x and g of x are inverses, and I'm not going to worry about showing it graphically. So, cool. These are notes for y'all to keep. I don't want y'all to worry about graphing example A and example C here. Just make sure you followed along on all this. If you can't print it off, follow along on a separate sheet of paper. Should be pretty simple to follow along. And I will post a worksheet that y'all will be doing. Please, when I post it on Schoology, pay attention to the directions because there's like, I know last time I posted some directions with it and it wasn't even like a lot of directions, but it was like, oh, just like for this problem, just pretend that this variable is a y, but like half the people just ignore that. So please pay attention to that. All right, so that's all. Yeah. And there will be like another assignment, another lesson, probably like Wednesday, Thursday. All right. Keep up the good work, guys.